The first part or first organ truly is not an organ, but it's part of an organ. Sorry, I'm not sure why it's kind of so wonky looking up there on the screen, but it's a familiar friend of ours, the hypothalamus, which we've previously learned quite a bit about. Major link between our nervous and endocrine systems. In our central nervous system lecture, when we talked about the brain, we learned about all of those different things that our hypothalamus does. And one of the things that was listed, I think it was like the very first or second bullet, was the fact that it produces hormones and therefore regulates the endocrine system. And there are cells within the hypothalamus known as neurosecretory neurons that secrete at least 9 different hormones. Okay, 7 of those hormones are classified as either releasing or inhibiting hormones, and that affects what they do, or that relates to their effect on the anterior pituitary. In other words, if it's a releasing hormone, it is going to tell the anterior pituitary to release a hormone. If it's an inhibiting hormone, it inhibits the release of a hormone from the anterior pituitary. Okay, and the regulation of these hormones, those inhibiting and releasing hormones from the hypothalamus, typically regulated by negative feedback. Okay, now there's a very cool feature that exists between the hypothalamus and the anterior pituitary, and that is the presence of what we call portal veins. Okay, now I'm not really going to get into great detail about portal veins, but this allows direct flow of those 7 hormones to travel from the hypothalamus to the anterior pituitary before that blood goes anywhere else. So those hormones go by way of these 2 blood vessels directly to the anterior pituitary. That's different than anywhere else, because typically when hormones are released, whether that's from the anterior pituitary or the posterior pituitary, for example, those hormones actually get carried to the heart and then back out of the heart before they go to their target organ. So it's nice because the hypothalamus releases the hormones. They don't have to then jump in the blood, get carried to the heart, and then back up into the brain. Instead, these 2 blood vessels allow for direct flow of blood and direct carrying of those hormones directly to the anterior pituitary. Notice there is not that same connection that exists between the hypothalamus and the posterior pituitary. The connection between the hypothalamus and the posterior pituitary is much different than the connection between the hypothalamus and the anterior pituitary. In fact, you can basically just call the posterior pituitary an extension of the hypothalamus, and we'll see that here in a little bit as to why that's the case. Okay. So hypothalamic hormones carry directly to the anterior pituitary via portal veins. Those specific hypothalamic hormones then bind to receptors on the specific anterior pituitary cells, releasing or regulating the release of the hormone they produce. Okay. Whereas the cell body is in the beginning of the tracts of the neurosecretory cells located in the hypothalamus and in blood capillaries in the posterior pituitary gland, which we'll see in a couple of slides. So what are those 7 releasing and inhibiting hormones? Well, I've included a table here on this following page that lists them off. Okay, what we're going to do here for the remainder of this lecture is run through the different hormones of our body, learning what they do, who they act on, who secretes them, etc. So there will be several questions on the exam on Thursday about hormones. Okay, there are 4 kind of key things that I want you to know about hormones, and I'll list them off right now. Okay, so when it comes to hormones, these are 4 very important things that you want to know. Okay, first of all, who secretes it? So in the case of those, it's all the hypothalamus. Okay, its principal action or actions. Come on, focus. So what does it do? If you want to call it action, or come on, this thing hates me some days, I swear. Principal action. Oh my goodness. How about I do this? I'm just going to type it. Not to mess with that stupid thing. So, once again, who secretes it? principal action or actions, all slash effect or effects. Okay. Let's see. The third one, I'm going to put them in the correct order here. Secretes it, principal action, stimulus for secretion. So in other words, what causes its release? There, that's a good size. And then target organ. So in other words, who is it acting on? Those are the four things that you'll want to know. Now, for some hormones, I don't give you all four things. So sometimes it's kind of this one. I just don't even tell you what triggers the release of it. Okay. But for most of them, you know, you're always going to know who secretes it, what it does, and who it targets. Okay. So going back to our lecture here. First of all, right at the top of the page, hypothalamic hormones. So that's who secretes it, hypothalamus. Acts on the anterior pituitary, that's telling you who is it targeting. Okay. And then principal effects is listed here in our table. What's missing, once again, I don't always give this to you, is the stimulus for secretion. So for these 7 hormones, you only need to know 3 out of those 4 things. Now, on Canvas, if you go in, and I printed this off for you guys here in Highland or in Wamigos, not Atchison, sorry. You go into Canvas though, if you aren't here now. If you scroll down, there's this link right here, hormone spreadsheet. I found this, I didn't create it, I found it. It's pretty darn close to exactly what you want for these hormones. As soon as it opens, let's download it, maybe that'll be faster. There we go. Okay, so looking at this table, the hypothalamus is the organ or gland, and then the hormones listed here in the second, the target tissue, and then principal action. So what's missing would be stimulus for secretion, which, like I said, you don't always have to know. In the case of those 7 hormones, though, they don't break them off into different levels. So they only have one box here for all 7 of those hormones. So it's not a perfect table, but for like the hormones that we're about to talk about, the anterior pituitary, each hormone is its own separate row, tells you who it's targeting, what it does. So very handy, and it goes through basically all of them that we'll run through here this afternoon. So use that to help you study, or you can create your own. I've had students make their own table or a spreadsheet or whatever. Okay. So what are those 7 hypothalamic hormones that act on the anterior pituitary? Once again, they're all either a releasing hormone, like this very first one, or an inhibiting hormone. If it's releasing, it promotes the release of a hormone from the anterior pituitary. If it's inhibiting, it inhibits the release of a hormone from the anterior pituitary. The first one, thyrotropin releasing hormone, tells the anterior pituitary to release thyroid stimulating hormone. TSH is the abbreviation for that. TRH is the abbreviation for thyrotropin releasing hormone. I'm not ever going to ask you to know abbreviations. There's going to be a lot of abbreviations that we'll run through. I'll always give it to you in the lecture, but I'm not going to expect you to know it on the exam. If I do use any of these on the exam, what I would do is the very first question where you might see thyroid stimulating hormone, I'd put in parentheses TSH, and then maybe later in the lecture or later in the exam, I'd use TSH, but I don't expect you just to know the abbreviations. And corticotropin releasing hormone promotes the release of adrenocorticotropic hormone from the anterior pituitary. Gonadotropin releasing hormone promotes the release of two different hormones from the anterior pituitary: follicle stimulating hormone, luteinizing hormone. Prolactin releasing hormone promotes the release of prolactin. Prolactin inhibiting hormone inhibits the release of prolactin. And then the last two do the opposite of one another. Growth hormone releasing hormone promotes growth hormone secretion. Growth hormone inhibiting hormone inhibits growth hormone secretion. Okay. So those are the 7 hormones. It's pretty straightforward. The principal effects, that's something that you're going to want to know for all these hormones, especially what they do. Okay, that's the biggest and most important thing, along with who secretes it. Those are kind of 2 things that I would definitely want you to know. And then the other 2 things, who's it targeting and stimulus with secretion. Sometimes I do, sometimes I don't really care so much about that. But I'll basically tell you what you should definitely know. So those are the hormones that are released right here that then are carried to here. Now, if I go back, I said that there's 9 different hormones that the hypothalamus creates. Well, listed here, there's only 7. And that's because there are 2 hormones that are created by the hypothalamus, but are transported down into the posterior pituitary for secretion. So the hormones that we'll find out that the hypothalamus creates, the posterior pituitary release, completely different than the hormones between the hypothalamus and the anterior pituitary. Speaking of the anterior pituitary, let's talk about it. A true and major endocrine gland with profound actions within the body. Once upon a time, used to be thought of as the master gland of the body because it regulates and does so many different things, but turns out it's actually number 2 in charge, and that's because your hypothalamus is number 1 in charge. And regulating the release of the hormones from the anterior pituitary are those 7 releasing and inhibiting hormones from the hypothalamus that we just talked about. Also affecting the release of hormones from the anterior pituitary is negative feedback. And there's 2 types of hormones that are anterior pituitary releases. Those that act on other endocrine systems are called tropic because they stimulate and regulate secretion of hormones by these other systems. So like adrenocorticotropic hormone, which literally has tropic at the end of it, triggers the release of another hormone, and that would be from the adrenal cortex. That's where that big term adrenocorticotropic comes from, because it targets the adrenal cortex. We'll get into all that here later in the lecture. Then you have hormones of the anterior pituitary that are called trophic hormones, and they promote growth. Okay, and that's what they're going to trigger: essential growth promoting effects on cells of target glands. Obviously, you can probably figure out the hormone literally called growth hormone would fall into that category. There are 5 distinctive hormone secreting cells that secrete 7 different hormones from the anterior pituitary. So you've only got 5 cells, 7 hormones. That means a couple cells secrete more than 1 hormone. Okay, we've got 4 out of those 7 hormones listed here on this page, and then the last 3 are listed on the next page. I didn't have room for all of them, as you can see here. Why? There's a lot of information listed for each of these. Yes, so there will be 40 questions over the endocrine system, and that's just because there's so much information. So many hormones that you're going to learn about. Okay, our first hormone, I usually just call it growth hormone or human growth hormone. It's abbreviated a couple different ways, GH. Sometimes they'll slap a lowercase h at the beginning of it, so it's like HGH. Also goes by somatotropin, and a lot of these hormones have a secondary term like thyrotropin, same thing as thyroid stimulating hormone. I don't care about their secondary name. Usually just growth hormone is perfectly fine. Okay. Its function is to stimulate secretion of insulin-like growth factors that promote growth and regulate aspects of metabolism. So its major job is to promote growth, but it does play a role in metabolization of things like carbohydrates and proteins. So it does play a role in like energy production. Okay, but it's going to promote growth as its first and foremost job, hence the name. But really, it's not going to trigger growth itself specifically, but it triggers the secretion of these IGFs, insulin-like growth factors, which actually are what promote the growth. So it's going to promote growth like indirectly, and we won't get into that. But we secrete a lot of this when we're kids, and that's what helps us get taller and gain weight and that kind of stuff. Grows our bones, that kind of stuff. The reason it's called somatotropin is it's because it's released by our cells called somatotrophs. Okay, and we release growth hormone in response to GHRH from the hypothalamus. So growth hormone releasing hormone is the most direct stimulus for secretion of growth hormone. Okay, now when do we release growth hormone releasing hormone? Well, in conditions like when we are hypoglycemic, which just is a fancy way to describe low blood sugar. Okay, we also secrete growth hormone in response to decreased fatty acids and increased amino acids in our blood. When we're in very deep sleep, whenever the sympathetic nervous system is active, so fight or flight, and by the release of hormones like cortisol, glucagon, estrogens, and insulin. So there's a lot of things that stimulate the secretion of growth hormone. Okay, things that you will absolutely want to make sure you know, because I'm not going to really focus on all of these. Okay, make sure you know that we release growth hormone in response to growth hormone releasing hormone. That's the most absolute direct way to trigger the release of growth hormone. And then I also want you to make sure you know we release it when we're hypoglycemic. Low blood sugar, hypo means low, glycemia for blood sugar. Okay, blood glucose, blood sugar, same thing. Now that's not the only hormone that we release when we are low in blood glucose, as we'll find out later in the lecture. TSH, short for thyroid stimulating hormone, also goes by thyrotropin. Like I said, don't worry about that other name. It stimulates the synthesis and secretion of the thyroid hormones by thyroid cells. And the reason it also goes by thyrotropin is because it's released by cells called thyrotropes. Okay, so thyroid stimulating hormone does exactly what its name tells you. It releases, or it stimulates the thyroid to release thyroid hormones. Okay, we'll get into what those thyroid hormones are in a little bit. We release TSH in response to thyrotropin releasing hormone from the hypothalamus. That's the most direct. So it's just like growth hormone releasing hormone. TRH, thyrotropin, releasing hormone from the hypothalamus is going to directly stimulate the secretion of the thyroid stimulating hormone. Okay, we also would say that when our blood is low in T3 and T4, or when our basal metabolic rates are low, we would be releasing TSH. And that's because T3, T4, those are the thyroid hormones, and they affect your metabolism. And so that's why those trigger the release of TSH. Main thing, make sure you know TRH, thyrotropin releasing hormone, is what stimulates the release of thyroid stimulating hormone. Okay, follicle stimulating hormone, along with luteinizing hormones, those together are what we call the gonadotropins. Okay, and that's because they affect our gonads. The gonads are the fancy ways, or that's the fancy way to describe your testes in men, and the ovaries in females, the primary sex organs. Okay, both of those are secreted by the same type of cell, gonadotrophs, in response to gonadotropin releasing hormone from the hypothalamus. So the stimulus for secretion of both FSH and LH is gonadotropin releasing hormone from the hypothalamus. They have the same stimulus for secretion. Okay, so what does follicle stimulating hormone do? Well, it's going to have to do two different things. It's going to do something for men. It's going to do something for women. In females, it stimulates the ovaries to initiate the development of oocytes. Oocytes are the eggs, okay, growing what we call ovarian follicles, and we'll get into all this stuff later in the semester. Okay, follicles are these bubbles with the eggs inside, and it stimulates the follicular cells in the ovaries to secrete estrogens in females. So that's the principal actions in females. In men, it stimulates the testes to promote sperm production. So it helps with promoting sperm. Okay. Luteinizing hormone is going to help stimulate ovulation. That's probably its most well-known function, which is when the egg is released into the fallopian tubes, because that follicle structure surrounding it has broken open. In doing so, that forms what's called a corpus luteum, which then is going to secrete progesterone and estrogens. And this is all once again taking place in the female ovaries. Okay. So those are female actions. In men, in the testes, okay, it helps stimulate testosterone production by Leydig cells. Leydig cells are the cells in the testes that produce testosterone. So in other words, LH stimulates testosterone production. Okay. So we will talk a lot more about these two hormones along with the hormones that are released as a response. So like estrogens, testosterone, progesterone. We'll get into all this later in the semester when we start talking about reproduction. That'll be the actually very latest part of the semester because we talk reproduction in our very last week of class. Okay, other hormones. Three other hormones from the anterior pituitary include prolactin, adrenocorticotropic hormone, and melanocyte stimulating hormone. Prolactin, think of that as it promotes lactation. Okay, I think that's just the easiest way to remember what it does. And lactation is just a fancy word for milk secretion. Okay, so in other words, it tells the mammary glands of a breastfeeding mother to release her milk, to secrete her milk. Okay, the cells that produce prolactin are called lactotrophs, and I'm not going to ask you to know any of these names of the cells, even though I've listed it off. I'm not going to ask you to not know that. Okay, stimulus for release for prolactin, pregnancy, and after pregnancy by prolactin releasing hormone from the hypothalamus. So prolactin releasing hormone triggers a release of prolactin. Pretty straightforward there. Obviously, females are not always breastfeeding and men are never breastfeeding. So does it have a role in those other people? Okay. Well, we know for sure in men, we're not sure. Okay. And by that, I mean, the function of prolactin in men is unknown, but hypersecretion, so too much of it, can be associated with erectile dysfunction. So can have a obviously not good side effect. Okay. Adrenocorticotropic hormone, I mentioned that a little bit ago. If you break down that really long word, has kind of three really different parts. Adreno for adrenal, cortico for cortex, tropic because that's the type of hormone it is. So who does it target? The adrenal cortex. What does it stimulate? Secretion of glucocorticoids, a type of hormone. Actually, several hormones, but mainly cortisol, which we'll talk about in a little while. The cells that secrete adrenocorticotropic releasing, or excuse me, not releasing, but just hormone, they are corticotrophs. And that's because, or that's why the other name for it is corticotropin. Okay, we release ACTH, I'm just going to say that so I don't have to say the whole word out, is the stimulus for secretion is corticotropin releasing hormone from the hypothalamus. So corticotropin releasing hormone triggers the release of ACTH from the anterior pituitary. Now, cortisol, as we're going to find out later in the lecture, is our stress hormone. So we release cortisol as a result of this. So in other words, whenever stress is going on, we release cortisol, and that only occurs because we release this. So stress-related stimuli trigger the release of this. Okay. Now, when you think of stress, you might just automatically assume like mental stress, like a test in 2 days over the endocrine system in the sensations lecture. But stress is just anything that impairs homeostasis. So like being low in blood sugar, hypoglycemia, having physical trauma, so like a broken ankle. Okay. Stress can be good, as we'll find out later in the lecture. So just any stress-related stimuli can trigger the release of ACTH. The final hormone, melanocyte stimulating hormone, has an unknown role in humans, but there is a set of receptors in our brain that are sensitive to melanocyte stimulating hormone, and that suggests it may influence your brain's activity. Okay, there's very little circulating MSH in humans, but if you actually were to administer it for several days, so this would be in a lab in a experimental situation. You couldn't obviously do this at home, but it would trigger a darkening of the skin, which should make sense for those of you who remember from anatomy class. Your melanocytes in your skin are what produce melanin, which causes you to tan up and gives you your skin pigment. Okay. Melanocyte stimulating hormones released by the same cells, corticotrophs, as ACTH. Okay. If there are excessive levels of corticotropin releasing hormone, that will stimulate its secretion. But for the most part, what you just want to know from melanocyte stimulating hormone, we don't really know what it does. Now, table 18.4 just summarizes those 7 different hormones. It gives you who the hormone is or what the hormone is, who's it targeting, principal actions, okay? And what's nice is that, I'm telling you all 4 of those things because at the top, who secretes it is listed right there. So there's the 4 things. I guess not the 4 things. You're still missing the stimulus for secretion, but 3 out of the 4 things are listed there. Here's just another illustration showing you how it all works. Once again, those 7 hormones from the hypothalamus must be released first, whether that's a releasing hormone or an inhibiting hormone, carried directly to the anterior pituitary, which is either going to trigger or inhibit the release of those various hormones from the anterior pituitary. And then you can see who's being targeted by those hormones at the bottom. Now, in the case of both the hypothalamus and the anterior pituitary, negative feedback is going to influence the secretion of those hormones we just mentioned. Okay. In an example on the right, we show cortisol at the very bottom, which we said is our stress hormone. Well, we release cortisol as a result of 2 hormones that we just talked about. Corticotropin releasing hormone from hypothalamus, corticotropin or adrenocorticotropic hormone from the anterior pituitary. So if cortisol levels are elevated, negative feedback can occur at both the hypothalamus and the anterior pituitary, which would prevent more cortisol release. So in other words, it would prevent too much cortisol from building up in the blood. And so it would stop it at point A and point B where the secretion originates. Now, what we're going to do as we roll through this lecture is talk not only about what hormones do for us, but what can happen if hormones are not secreted enough in our body or if we secrete too much. So I've kind of picked and chose some of the most important ones or most common, or I don't know, the funner ones to learn about. First one, what we call giantism. You can also see it sometimes listed as gigantism. This is going to occur in growing humans. Who are growing humans? Kids. Okay. So people that aren't as an adult. Okay. And typically what can cause giantism is a tumor on the pituitary or the hypothalamus. The key with giantism is it leads to excess secretion of growth hormone when they're a kid, so they grow really tall. Now, I'm not saying growing really tall isn't they're like 6'3", 6'4", 6'5", nor am I saying that they're like 7 foot. Okay, sometimes they can be like a gigantic person. Okay, down here at the bottom left is a picture of a very famous, very large individual standing next to a model. This guy's not alive anymore. The tallest person ever recorded in human history. And then there's a stick on the left here measuring their height. If you don't recognize who this is, his name's Shaquille O'Neal, one of the biggest humans walking on Earth, stands over 7 feet tall. Look at him next to this guy. Looks like a baby. Okay. This fellow was almost 9 feet in height. So I'm not talking a little tall. I'm talking excessively tall. Okay. Crazy, crazy height. Okay. If you've ever heard of Andre the Giant, another great example of somebody that had this. Okay. Here's a crazy image of Andre the Giant's hand holding a beer can. That's a regular sized beer can in his hand. Isn't that insane? Now, sounds really cool to be huge, right? Unfortunately, these people really don't live healthy lives. It's not good to be that big. Okay. Puts the body in a lot of issues, a lot of joint issues, a lot of cardiovascular issues, pumping blood all over those places is very difficult. Hard on the heart. They don't live a long, healthy life either. Basically, the opposite of giantism is dwarfism, caused by absence or reduced levels of growth hormone during childhood. Okay, typically causes children to be short in stature. But the wonderful thing about this type of dwarfism is it's pretty easy to treat because you can get synthetic forms of growth hormone. Okay, and therefore, the person can grow to a normal height. Now, when you think of dwarfism, more than likely you're thinking of a genetic form of dwarfism. Where there is no way to treat it with synthetic hormone. This is specifically called pituitary dwarfism. There's other forms of dwarfism. This is specifically pituitary. And then acromegaly, I believe is how you pronounce that. This is key here. What happens if you excessively secrete growth hormone in adults? Okay, so with giantism, this is in kids and adults. This is what causes acromegaly. Bones that no longer can grow in length due to fusion or closure of the epithelial plates tend to grow in width. So you don't get taller, you get wider. And this can lead to something like what this fella has, where there is obvious deformity. Their mandible's really big and protruding. A lot of times they have this big bulge in their forehead. Their fingers, their toes get really, really big and bulky, and it can be very painful. But you're just looking at the picture, the individual doesn't really look like a traditional face should. Okay. So very unfortunate condition. All right, so that's the anterior pituitary. Let's talk about the posterior pituitary. Your posterior pituitary is technically not a true endocrine gland because it does not contain true secretory cells. And that relates to the fact that it does not even synthesize hormones. It does not make hormones. What it does is it takes two hormones that the hypothalamus make and stores them until it's time for release. Okay, here's what happens. So there are these two different types of neurons in the hypothalamus that have axons that project down into the posterior pituitary. Okay, these two types of neurons are called neurosecretory cells, paraventricular, supraoptic. Okay, the hormones are created by the cell bodies of these neurons, and then those hormones are carried down through the axon of the neuron into the posterior pituitary. So earlier I said that the posterior pituitary is just an extension of the hypothalamus. You can see why. It is truly just an extended part of the posterior pituitary, or of the hypothalamus. Those two hormones include oxytocin and antidiuretic hormone. We've talked already this semester about oxytocin. Okay, in fact, we talked about it in our very first lecture when we first described positive feedback. Okay, oxytocin is the hormone that causes the cervix, or is going to cause the uterus to contract more forcefully when the cervix stretches. Okay, not only does it help with labor, but it's also going to promote lactation. Okay, the first bullet there, enhances smooth muscle contraction while uterus responsive stretching of the cervix, is what we talked about earlier in the semester. Okay, the second bullet is kind of a more brand new thing. It stimulates milk ejection from mammary glands in response to mechanical stimulus provided by a suckling infant. So when that baby starts sucking on the nipple, that promotes the ejection of milk. So going back a couple slides, we said prolactin promotes milk secretion, whereas oxytocin promotes milk ejection. So it's a very subtle difference, but it is a difference nonetheless. Okay. Now, you may have heard of the drug Pitocin before. It is sometimes given to females that are slowly going through labor and things aren't progressing, or if a female wants to be induced, they can give synthetic Pitocin. Synthetic oxytocin is just what Pitocin is scientifically known as, and that's what can trigger labor. And that's because of what happens here. It causes the wall of the uterus to contract, pushing the baby downward. Okay. Obviously, like with prolactin I mentioned earlier, not every female's breastfeeding, not every female is going through labor, and obviously men do neither of those things. So what does it do? Well, same thing. We're not 100% sure, but research on animals does suggest it may have to do with caretaking behaviors as well as feelings of sexual pleasure. Antidiuretic hormone, ADH, is a hormone that does the opposite of what a diuretic does to you. If you've never heard of a diuretic, okay, a very common example of a diuretic is alcohol, where the more alcohol you drink, the more you pee. Okay, that's what diuretics do to you. Okay, antidiuretic hormone decreases the production of urine, so it makes you pee less. Okay, by causing the kidneys to return more water to your blood. Okay, we secrete antidiuretic hormone when we have a high blood osmotic pressure, which is just another way to describe low blood volume. If you really simplify things, dehydration. Okay, when your water levels are low, or like when you are low in blood because you're hemorrhaging, you're bleeding, you're going through diarrhea or excessively sweating. Okay. What's common is for a person to wake up after drinking a whole bunch of alcohol and feel the effects of a hangover. Okay. That's because alcohol actually suppresses the release of this hormone. So you do pee a whole bunch, and therefore the more you drink, the more you pee, the more dehydrated you are the next day. And once that alcohol is out of your system, then you'll release this hormone to try to get as much water and keep as much water in your body as possible. Okay. One way to also lose water is to sweat. So antidiuretic hormone also decreases the water you lose when you sweat. Okay. We'll talk about antidiuretic hormone again later in the semester for its role in causing our blood pressure to go up. It does so by causing constriction of our arterioles, which makes them basically pinch shut, and that makes your blood pressure go way up. And that's why it's also known as a hormone called vasopressin. It causes a vasopressor reflex. And you may have heard of like drugs called pressors or pressins, and that's a type of drug that will make your blood pressure go up, and just like ADH can make it do. All right, our largest endocrine gland in the body is the next gland here, our thyroid. Composed mostly of sacs called thyroid follicles, each of which is filled with a type of fluid called colloid, lined by a simple cuboidal epithelium of follicular cells. Not that that's really important stuff, but I mentioned it nonetheless. Two major thyroid hormones exist, which have funky long chemical names, tridithyronine, tetrahydrithyronine, that you'll never, ever have to spell or say. T3 and T4 is absolutely perfectly fine. Thyroxine is another way to say T4, but T3 and T4 is how I want you to know them. Okay, the primary thing about them is what they do, and that's increase your body's metabolic rates. They increase your metabolism. Okay. They do so by increasing the rate of oxygen consumption under standard or basal conditions. Basal conditions being like when you wake up, you're still resting and you're fasting. So like right in the morning when you haven't eaten for 8-10 hours, you're not even out of bed yet. Okay, but you're awake sitting on your phone. Okay. So that's what the thyroid hormones do. They increase the metabolism of carbs and lipids and proteins. Okay. what we do with those carbs, lipids, and proteins, we make ATP from them using oxygen. So it helps promote aerobic cell respiration. When BMR increases, the metabolism of carbs, lipids, and proteins must increase. There's a second major effect of the thyroid hormones, and it's to stimulate the sodium potassium ATPase pumps, which use a lot amount of ATP to continually eject sodium from the cytosol into the ECF and potassium into the cytosol against their concentration gradients. Remember, the sodium potassium ATPase pump is an example of primary active transport. In doing this process, this is going to help raise your body temperature. Okay, as we've learned early in the semester, anytime chemical reactions are taking place, our body produces heat. Okay, and pumping those sodium and potassiums against their concentration gradient produces a lot of heat. And this phenomenon is called the calorogenic effect. This is something that we also do when we're cold, aside from shivering. So we've talked about shivering since the very beginning of the semester, that negative feedback response when we're cold, like on a morning like this morning was. What we're also doing internally, aside from that shivering, is releasing T3 and T4 to increase our metabolism and to increase our sodium potassium pump action, which makes our body temperature go up. Other things these thyroid hormones do: stimulate the synthesis of proteins and use of glucose and fatty acids for ATP production, enhance the actions of our catecholamine hormones, that we'll find out what those are in a little bit. And thyroid hormones also accelerate body growth. Down at the bottom are things that trigger the release of these hormones. The most direct thing that triggers the release of T3 and T4 is the release of TRH from the hypothalamus, which then triggers the release of TSH from the anterior pituitary. So as we learned earlier, the hypothalamus releases a hormone that then tells, in this case, the anterior pituitary to release TSH, and TSH then tells the thyroid to release T3 and T4. Okay. So why would we release TRH? Well, if our blood levels are low in T3 or T4, or if our metabolism is low. Okay. And then other things that can trigger the release of T3, T4 would be increases in ATP demand, like being in a cold environment, hypoglycemia, which we learned earlier is low blood sugar, high altitude, pregnancy, also increase the secretion of thyroid hormones. So those are all just examples of stresses that can trigger the need for ATP, thus trigger the release of T3 and T4. Now, the synthesis, storage, and release of the thyroid hormones is pretty unique because this is the only gland in our body that stores T3 and T4 or its hormones in large quantities. And it is a really complicated series of events. I'll kind of just run through it really quick. I'm not going to ask you to know any of this on the exam just because it's so complicated. I mentioned earlier in the lecture that T3, T4 are the only hormones that involve iodine as part of their structure. And so the very first thing is we trap iodide, the ion form of iodine, and actively transport them out of the blood into the cytosol, so into our cells, okay, those cells of the thyroid. Okay. Then we synthesize thyroglobulin, TGB, which is a type of protein, okay, that's released into the lumen of the follicle, okay, into the colloid, the fluid. Okay. Then we oxidize the iodide. Okay, in order to bind tyrosine, they must undergo oxidation to form iodine I2. Okay, iodination of tyrosine takes place next. As those I2 molecules form, they react with tyrosines of GGBs to form monoiodityrosine and diiodityrosine, okay, which is collectively known as colloid. Okay, mono, as we know, means one, di means two, right? Well, if you add 1 and 2, what do you get? 3. If you add 2 and 2 together, you get 4. So that's what happens. Step 5. That's where T3, T4, those names come from. Okay, and that's what's taking place up here with number 5. Number 6, we're then bringing those hormones back into the follicular cells. Okay, that's through endocytosis. or pinocytosis, specifically a form of endocytosis. And we hold on to them, and then it's time to release them out into the blood. Since these are lipid-soluble hormones, they must be bound to a transport protein. That's what the TBG is, to help them transport throughout the blood. And then that's number 9. Or 8, excuse me, not number 9. So a lot of complex, crazy things happening. But like I said, you don't need to know any of that for the exam. What you will need to know, though, is included on this next page. All right, just like with the anti-pituitary, hormones released from the thyroid can be subject to imbalance, leading to severe consequences. First two basically are the opposite of one another. We've seen this prefix hyper and hypo, or these prefixes hyper and hypo, several times before. Hyper means high, hypo means low. Hyperthyroidism, therefore, is a disorder characterized by too much secretion of the thyroid hormones. Okay, and therefore, since T3 and T4 increase your metabolic rate, the person will have a very high metabolic rate, leading to things like weight loss, irritability, and various cardiovascular changes. This happens a lot with people that have Graves' disease, which is an autoimmune disorder caused by abnormal antibodies against TSH receptors, and therefore results in excess thyroid stimulation. Many individuals with Graves' disease suffer from what's called exophthalmos, which is what this lady has here, where there's a peculiar type of swelling or edema behind the eyes that makes the eyes kind of pop out. And, you know, she's got her eyes wide open, but it's pretty wild how far out they can stick out from the fluid that's behind them. Some individuals with hyperthyroidism also can develop what's called a goiter, which is a very large thyroid, like what's shown over here on the left. Okay. Hypothyroidism is where there's a low secretion of thyroid hormones, okay, which can be caused due to issues at the thyroid level, at the pituitary or the hypothalamus, and typically results in a lower BMR. These people a lot of times are going to be much heavier. Okay, you hear about people having thyroid conditions being obese. Okay, it's not typically hyper, but hypothyroidism. That's the culprit. Okay, other things that hypothyroidism can cause would be mixed edema, consisting of thick skin, puffy or husky face, and coarser, thicker hair. And then cretinism, which is kind of a traditional term. Congenital hypothyroidism is more of the kind of common term now. A thyroid deficiency in infants and children. So it is really unfortunate because it results in dwarfed and mentally deficient children due to abnormal brain development. It used to be kind of a slang to call someone a cretin because they're like ugly or gross. Well, that's a really mean thing if you understand what cretinism is. So if that's a term you've ever heard or used before, don't use it. It's not good. All right, there is a third hormone that your thyroid produces, and that hormone is called calcitonin. Based on its name, I would assume it's pretty easy to recognize what it's going to affect. Calcium. Produced by a different type of cells in the thyroid called parafollicular cells or C cells. Its job is to lower your blood calcium when it is high, a condition called hypercalcemia. There's that prefix hyper again. Okay. It inhibits what we call bone resorption, which is a fancy word for the breakdown of bone, which is done by decreasing the activity of osteoclasts, which are cells in our bones that break down our bone extracellular matrix. Okay. We have in our body osteoclasts and osteoblasts. Osteoclasts basically break down the calcium out of bone and release it into the blood. Okay, well, if your blood is already high in calcium, you don't want these guys continually doing that. Okay, osteoblasts do the opposite. They take the calcium from the blood and make bone out of it. Okay, well, we'd want those guys to be active, and we want these guys to be inactive. Okay, and that's going to help lower the blood calcium levels. Okay. Calcitonin also accelerates the uptake of calcium and phosphates into bone matrix, which is basically what I was just talking about, what our osteoblasts do. Make bone out of calcium and phosphate ions. So that's the thyroid. Our next glands are the parathyroids, which are on the backside of our thyroid glands. Typically, we have 4 total parathyroid glands, each of which is about the size of a pea. Not very big at all, but very important nonetheless. The principal cells of our parathyroid glands are literally called chief or principal cells, and they secrete the most straightforward named hormone we will see. If on the exam I ask you who secretes parathyroid hormone and you don't put the parathyroid glands, I will die a little inside. Parathyroid hormone, also goes by parathormone, is actually the major regulator of calcium, but also magnesium and phosphate ions in the blood. We just learned that calcitonin is released when our blood calcium is high. Well, parathyroid hormone is released when our blood calcium is low, what we call hypocalcemia. So parathyroid hormone and calcitonin are an example of antagonistic hormones where they produce opposing effects. This hormone, this time, increases the number and activity of osteoclasts, therefore increases the increases or elevates bone resorption or bone breakdown, which therefore increases blood calcium levels. Okay, so it helps increase the breakdown of bone to release calcium into the blood, makes your levels go up. Okay, it also acts on your kidneys to slow the rate at which calcium magnesium ions are lost from our blood into urine, as well as increasing the release of phosphate ions in urine as their levels increase during bone resorption. So in other words, it prevents us from peeing out too much calcium and magnesium, which would lower your blood calcium levels. Okay. There is a third hormone that regulates our calcium levels, and that is calcitriol. Okay. PTH promotes the formation of this hormone. Now, keep in mind, I'm talking about calcitriol on the slide that says the parathyroid glands at the top, but know that calcitriol is not released by the parathyroid glands, it's released by the kidneys. Calcitriol, released by the kidneys, is actually the active form of vitamin D, which we all know we can get from like our sun or vitamin D milk. It is also going to help increase calcium and magnesium levels in our blood by helping us absorb it from our GI tract. Okay, so in other words, like if you drink milk and your calcitriol levels are high in the blood, you're going to pull more calcium into your body from your intestines and your stomach. Make sense? Okay. Now, the regulation of our blood calcium levels using calcitonin, PTH, and calcitriol is going to work by negative feedback, but this is the first example of negative feedback that doesn't involve the pituitary gland. And here's an illustration to show you how complicated, but how simple it really truly is. So I'll start here at number 1, high levels of calcium in the blood. So this was hypercalcemia. Triggers the release of CT. CT short for calcitonin, which is going to help lower blood calcium levels. Okay, so it does what it does to lower blood calcium levels. Let's say we release enough calcitonin that our blood drops in calcium levels to a point where we actually have gone a little low. So we become hypocalcemic. Okay, and therefore we release PTH from the parathyroids. That's what these 4 green dots are on the backside of the thyroid. PTH, as we know, increases calcium levels itself, but it also tells the kidneys to release calcitriol to help further increase calcium levels. And so we could start the whole process over by actually becoming hypercalcemic again, demonstrating just how fine-tuning works with things like blood calcium levels and trying to keep those levels very, very close to that set point that we really like. Okay, our next glands are the adrenal glands. A lot of similarities with the adrenal glands to the pituitary. Not that there's an anterior and posterior adrenal gland, but that there's 2 distinctively different parts, what we call the adrenal medulla and the adrenal cortex. Now keep in mind there are 2 adrenal glands, so each adrenal gland has a cortex and a medulla, but they are distinctly very different from one another. Okay, the adrenal cortex comprises about 80 to 90% of the gland and has 3 different zones, each of which is responsible for producing different steroid hormones. We'll get into those more on the next page. The adrenal medulla, the inner region of our adrenal glands, is something that we've already talked quite a bit about. It is modified sympathetic ganglion of the autonomic nervous system. It's just an extension of the sympathetic nervous system. In fact, we've talked all about these 2 hormones, what we call the catecholamines, epinephrine and norepinephrine, or adrenaline and noradrenaline, secreted in response to fight or flight stressful situations that trigger things like increases in blood pressure, increases in heart rate, increases in contractility, dilation of your airways, dilation of your pupils, et cetera, et cetera, et cetera, et cetera. We've already talked all about this. We learned earlier that 80% of what's secreted from the adrenal medulla is epi, 20% norepinephrine, and then I didn't even include a trace amount of dopamine just because there's not very much of it. I'm not going to get into any more because we spent half a class period or more talking just about epi, norepi, and the sympathetic nervous system. So let's talk about the other hormones of the adrenal glands. And these are strictly from the cortex. Okay, I've got 3 different types of hormones, and those are each released by a different zone from the adrenal cortex. The first zone is the outer, what we call zona glomerulosa, which secretes a set of hormones collectively called the mineralocorticoids. And they are called the mineralocorticoids because they affect homeostasis of our minerals. So what are our minerals? We'll get into that. The only hormone of those mineralocorticoids that you need to know is aldosterone, which is nicknamed the salt retaining hormone because that's what it helps us do. It helps us retain salt. And it regulates the homeostasis of the mineral ions, sodium and potassium. It also helps adjust your blood pressure and your blood volume. Blood volume being the amount of blood that you have. Blood pressure is the force of that blood against the walls of our blood vessels. It also promotes the excretion of hydrogen ion by our kidneys, so therefore helps remove acids from the body. So it plays a lot of different roles. Okay. The secretion of this hormone is regulated by one of the most complicated things that we'll talk about later in the semester. Here's an illustration of that mechanism, what's called the renin-angiotensin-aldosterone mechanism. It involves not just the adrenal glands, but also the liver, the kidneys, even involves cells in the lungs, where an enzyme called angiotensin converting enzyme is produced. It's a crazy, I mean, look, there's 12, 15 steps here, a lot goes on. And we'll get into this much later in the semester, okay? For now, we'll just kind of leave it at that. We've got enough to worry about. I don't need to introduce something that complex on top of this. Your glucocorticoids are secreted by the zona fasciculata, which is the middle part of the cortex. Based on its name, pretty straightforward, I would think. It's going to help regulate our glucose homeostasis. I've already mentioned this hormone today, cortisol. Told you earlier is our stress hormone because it helps increase our body's resistance to stress. Okay, what do you need to be able to resist stress? Energy. Energy in the form of ATP. And how can we make ATP? From traditionally glucose and fat, carbs and fats. Okay, so cortisol is going to affect your carbs and your fats specifically, as well as proteins in order to give you energy. Okay, so how's it going to work? It increases your blood glucose supply for tissues, mainly the brain and heart, so that you can combat that stress. It does so by promoting the catabolism. Catabolism, remember, is breaking things down of proteins and stimulating the conversion of the resulting amino acids to glucose, a process known as gluconeogenesis. It also stimulates lipolysis, which is the breakdown of triglycerides or fats, releasing fatty acids into the blood. Now, I'm going to jump over to my Word document again. I'm going to create a new one. I don't really need to, but I will. And I'm going to type up 6 pretty big words. And these 6 big words we will see several times here in the next few weeks, which includes this lecture, but also future lectures. So if I can turn sideways. Okay. The first word is not one of those that was just listed there. This word is very important. It's called glycolysis. Okay. And this is the breakdown of glucose, ATP. The second term looks a lot like that. It's called glycogenolysis. Which is the breakdown of glycogen into glucose molecules. Our third word is going to be glycogenesis, which looks similar to those first two, but is the formation of glycogen from glucose molecules. Fourth word is called gluconeogenesis, which was one of those terms that you just saw in your lecture, is the formation of glucose from non-carbohydrate sources like fats and proteins. Then you have lipolysis, triglycerides. Okay, so you've got 4 that start with a G, 2 that start with lipo. Let's write those out and we'll talk about them. Some of these, I imagine, look familiar to you. I'm sure you've heard of glycolysis before. We've seen glycogenolysis. That was actually at the end of our somatic autonomic lecture. So was lipolysis. Some of those you may have never seen before, but that's okay. See them now, and we'll talk about them. All right, so going back to the functions of cortisol, it helps increase your blood sugar. It does so by helping form glucose from things like amino acids. Amino acids when we break down proteins. The proteins, amino acids are not a carbohydrate. That's a non-carbohydrate source. That process is called gluconeogenesis. That was the 4th term I put on the page. Okay. Literally translates to mean new glucose formation. Genesis, which you see at the end of several of those words, means to create or form. Whereas lysis, which you see like here with lipolysis, means to break down. Okay. Lipolysis means to break down triglycerides, release the fatty acids in the blood, and then we can use those fatty acids to make ATP. So cortisol promotes lipolysis and gluconeogenesis. Okay. What about these other terms and why did I type them up? Well, you'll see some of those here in just a couple of next slides. Okay. Once again, these effects increase the body's resistance to stress, which is why we call this hormone the stress hormone. Okay. Aside from doing that, cortisol also plays a part in inhibiting the effects of white blood cells participating in inflammatory responses. Okay. Unfortunately, this can explain why excess stress can impair the immune system. This is why if you get sick around finals week, it's because you're stressed and your body is more susceptible to catch a cold or the flu or something like that. Okay. You can get synthetic cortisol and other glucocorticoids as a medicine to treat overactive immune systems like asthma, allergies, autoimmune disorders. Okay. You may have heard some of those common terms before. Let me just Google some and you might recognize some of these terms. Synthetic cortisol. Synthetic versions of cortisol. Let's see, I'm just going to go to the first one. Maybe it doesn't have a list of them, but that's okay. You ever heard of cortisone, like a cortisone shot before? That's just synthetic cortisol. Okay. Now, whereas excess levels of cortisol can cause your body to become impaired as far as immunity, if you're low in your blood levels of cortisol, that will stimulate the release of CRH from the hypothalamus, which then promotes the release of ACTH from the anterior pituitary, which then stimulates cortisol release. Okay. So same situation we've seen several times. CRH, corticotropin releasing hormone from the hypothalamus, triggers the release of adrenocorticotropic hormone from the anterior pituitary, which then tells the adrenal cortex to release cortisol. The final hormones from the adrenal cortex are called the androgens, released by the zona reticularis, have masculinizing effects, make you more masculine. Okay. The only one that's actually important and is really only important in females is DHEA, promotes the female libido or sex drive and is converted into estrogens by other body tissues. When it comes to those that produce masculine effects in men, DHEA is not nearly as important as something like testosterone. Okay. So testosterone and DHEA in females, very similar in what they do, but I'm not even going to get really into great detail, nor does your textbook. So I won't really spend any other time of just what's listed there. Okay, your next gland truly is not a gland, but more of an organ, but it does contain glandular cells, is your pancreas. It is 99% built for digestive purposes. It produces a lot of enzymes that help us with digestion. Those cells are called acinar cells. They produce what's called pancreatic juice. We'll get into all that later in the semester when we talk about the digestive system. For now, we're just going to talk about the 1% of cells that produce the following 4 hormones. These are what we call pancreatic islet cells, or islets of Langerhans. There's 4 different cell types. Each secretes a different hormone. The first type of cells, alpha cells, secrete the hormone glucagon. And this is a case where I actually do want you to know which cells secrete what. So I do expect you to know what hormone is secreted by alpha cells, which hormone is secreted by beta, etc. Okay. Glucagon is a hormone that we release when our blood sugar is low. Once again, there's that prefix hypoglycemia, not to be confused with hypocalcemia. Hypoglycemia is low blood sugar, low blood glucose. Okay. If you want to remember it, this is an easy way to remember it. You secrete glucagon when glucose is gone. So in other words, when your blood glucose levels are low. Okay. We also secrete glucagon when we are in a sympathetic situation, like when we're exercising, fight or flight, running from a bear, yada, 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 as well as when we are following a really protein-heavy meal. Glucagon helps elevate your blood sugar by doing the following. It promotes the breakdown of glycogen to glucose in one of those of our 6 big words, glycogenolysis. If you break down that word glycogenolysis, literally has the word glycogen at the beginning and then lysis at the end. You don't remember, glycogen is the stored form of glucose. So it's just where you take a bunch of glucose and you stockpile it. Okay. Well, we break down the glycogen to release the glucose, and that makes your blood glucose level goes up. Okay. We also promote the conversion of amino acids into glucose. There's that same word that we saw a little bit ago. That process is called gluconeogenesis. Insulin and glucagon are antagonistic hormones. So in other words, glucagon elevates your blood sugar, insulin lowers it. We secrete glucagon when we're hypoglycemic. We secrete insulin when we're hyperglycemic, high blood sugar. Okay. It does the opposite. Instead of breaking down glycogen, it helps us form it. That process is called glycogenesis, okay, which literally has glycogen at the beginning and genesis at the end. So the formation of glycogen. It also can help us form our fats, a process called lipogenesis. Okay. And if I go back to my Word doc here, okay, lipogenesis was at the end, formation of fats and triglycerides. Glycogenesis was our, number 3, formation of glycogen from glucose molecules. So now we've seen the 5 things here at the bottom. The only one, and you won't see it, I went ahead and wrote it out, is glycolysis, breakdown of glucose to form ATP. And that's something that we do, like when our blood sugar, is moved into our cells to make ATP. So we'll get to that later this semester. Okay. So that's glucose, or excuse me, glucagon and insulin. Okay. Delta cells secrete the hormone somatostatin, which inhibits the secretion of insulin and glucagon and slows the absorption of nutrients from the GI tract. F cells secrete pancreatic polypeptide, which inhibits somatostatin secretion, gallbladder contraction, and secretion of pancreatic digestive enzymes. Meals that contain protein, fasting, exercise, and acute hypoglycemia would stimulate its secretion. Okay. Now, as far as hormones go, I do want you to know what somatostatin and pancreatic polypeptide do, definitely. But if you only had to study two hormones, glucagon, insulin, would be definitely ones you absolutely want to know. Here is an illustration showing you that relationship between insulin and glucagon. I'm not going to go through it, but on the left, they have low blood sugar, low blood glucose, hypoglycemia, secreting the alpha cells to secrete insulin. And then what it does on the right, it shows beta cells secreting glucagon when, sorry, I read it wrong. Hypoglycemia stimulates the secretion of glucagon from the alpha cells. High blood sugar, hyperglycemia, triggers insulin to be released. And that's kind of like that slide we saw a couple slides ago with calcium and calcitonin, parathyroid hormone, calcitriol, but specific for glucagon, insulin, and glucose. Now, our most common endocrine disorder is called diabetes mellitus, or as we just commonly call it, diabetes. There are 2 primary forms of it, both of which involve insulin. Type 1 and type 2 diabetes are the 2 major types, primary forms. Not the only forms. There's also like diabetes insipidus, gestational diabetes, which happens during pregnancy. But type 1 diabetes results from an autoimmune dysfunction where the immune system cells destroy the pancreatic beta cells, which means the person cannot produce their own insulin. People that are type 1 diabetic are described as, and I would write this down, insulin dependent, which means that they have to get synthetic insulin. Used to be, you'd have to go get a whole bunch of shots to inject the insulin. Now they do a lot of pumps. You get them where they stay on your body for several days and you can change them out over time. Type 2 diabetes is where there's an excess level of glucose levels in the blood, causing the cells to become, and I would highlight that last couple of set of words, insulin resistant. So the body produces the insulin, it doesn't respond to it. Basically, it's gotten so used to having high blood glucose levels that it doesn't respond to insulin as well. You guys know which one's more common? Type 2, and it is way more common. They used to use the terms adult onset and juvenile onset to describe these. Do you know which one used to be adult onset? Type 2. And type 1, therefore, was described as juvenile onset. Why don't they use those terms anymore? Because kids are a lot of times getting type 2 diabetes. And it's mainly due to the fact that it's lifestyle. Type 2 diabetics have on average, in most common situations, a poor lifestyle where they are overweight or obese. They don't get enough exercise. They don't eat good food. And that's what triggers the excess levels of glucose in their blood. The great thing is with type 2 diabetes, it can pretty much be treated
just by altering their lifestyle. Unfortunately, type 1 diabetes, you can't treat it by, changing your diet, changing your exercise levels. That is something that just, it can't be fixed that way. Whereas type 2, you can pretty much, you can't say you're cured from it. You never are cured, but you can pretty much, it's almost like putting it in remission. So unfortunately, it is something that's pretty much preventable, but it's very common.
Yeah, I'm sure there's a genetic component to it, like my dad has it. I'm sure there's a higher risk for me to have it, but it's not your parents have it, so you're destined to have it. Okay, our next organs are the gonads. I mentioned earlier the gonads are the organs known as egg and sperm, or not egg and sperm, sorry. I read egg and sperm as I was trying to talk, but are the ovaries in women and the testes in men. And I read egg and sperm because that's where they're produced. They produce the gametes, fancy word for your sex cells, sperm in men, eggs in women. But since they produce hormones, that's why we're talking about them here. The ovaries secrete the following hormones: estrogens, and that's plural on purpose. Although most people just say estrogen, it's actually more than one: estradiol, estrone. What do those hormones do? They are involved with the maturation of an ovum. Ovum is a mature egg. Estrogens also help prepare the uterus for possible fertilized egg to arrive there. The uterus becomes the womb, so that's where the egg that's been fertilized will, hang out and become a baby. Estrogens also promote the development and maintenance of secondary sex characteristics, as well as the closure of the epiphyseal plate. Secondary sex characteristics are, in females, like growth of the breast tissue, growth of pubic hair, that kind of stuff. Progesterone helps promote the storage of glycogen and growth of blood vessels in the endometrium, which is the inner lining of the uterus. Progesterone also helps grow secretory cells and mammary glands. Inhibin, which actually men produce in their testes, does the exact same thing in men and women. Inhibits the secretion of FSH, follicle-stimulating hormone, by the anterior pituitary. And then relaxin, just like inhibin, which name kind of tells you exactly what it does, relaxin helps relax. It's produced during pregnancy, increasing flexibility of pubic symphysis, which is a little piece of cartilage between the hip bones, so the hips kind of spread out a little bit more. It helps dilate the cervix during labor. It also inhibits contraction of the uterus, making it easier for a fertilized egg to implant in the uterine wall. Aside from inhibin, the testes produce testosterone, which before birth helps cause the testes to descend down from the abdominal pelvic cavity. Its primary job, though, is to help regulate sperm production. And just like the estrogens helps develop and maintain male secondary sex characteristics. So, facial hair and pretty much hair everywhere for guys. It also helps develop the, enlargement of the penis and the testes and that kind of stuff. And also helps close the epiphyseal plate. So stops growth and height. We'll talk more about all those hormones and those organs, like I said, later in the semester when we talk about reproduction. Okay, a gland that we've seen before and talked about before is our next gland here, the pineal gland. Consists of nerve gland pineocytes to secrete that function to secrete its hormone, that hormone being melatonin, an amine hormone derived from serotonin, which, as we learned earlier, helps to set our biological clock, which we fancily describe as our circadian rhythms. We secrete more melatonin at night when it's dark than when it's light, so it's thought to promote sleepiness. And that's illustrated here with our figure at the bottom, showing here where daylight can inhibit versus nighttime excites. And it's a process involving the autonomic nervous system with sympathetic stuff going on, but either we promote or release or inhibit the release of this melatonin into our bloodstream. Not so much of an issue here in Kansas, where
we're getting good amounts of light and dark during the day, but if you live somewhere like up in Canada or in Alaska, and certain times of the year where, it's, I think there's a city in Alaska that goes dark for like 2 months or something like that, and the sun never comes up. And then there's also periods of time where the sun never goes down. So 2 a.m. and the sun's still shining can really screw with you. So it can lead to seasonal affect disorder, where you're, depressed and that kind of stuff because your mood's just messed up because you're not sleeping. So people that live in those places have to really, get dark blinds and that kind of stuff so that their body's getting that melatonin production like they really need to. As always, I've mentioned this before, or as I've mentioned before, you can also buy synthetic melatonin to help promote sleepiness, like a lot of parents do, to get their kiddos to sleep.
Okay, the next structure is the thymus. The thymus is a gland that we'll talk about later in the semester, located between the sternum, or behind the sternum, between the lungs. It sits right on top of your heart. It produces a heck of a lot of hormones: thymosin, thymic humoral factor, thymic factor, thymopoietin. I don't care about each individual name. All I care about knowing is just those are the thymus hormones. Okay, so if you want to call them thymic hormones or thymus hormones, whatever, all of them are involved with maturation of our T cells. What are T cells? Well, they're fancily known as T lymphocytes, a very important type of white blood cell that destroys microbes and foreign substances. Okay, so what you'll have to know for the exam is that the thymic hormones help promote T cell maturation. That's basically the main takeaway. Nothing too crazy there. Thymic hormones may also play a role in slowing down the aging process, which is kind of cool. All right, we'll do this last slide and then I'll call it a day. Hormones from other endocrine tissues and organs. As mentioned earlier in this lecture, cells and organs other than those usually classified as endocrine glands can secrete hormones and have an endocrine function. The following table provides an overview of these structures, the hormones they release, and their hormone action. Some of them we did talk about. For example, if I look over on the table down under kidneys, there's calcitriol, but I didn't mention anything about renin or erythropoietin. Other hormones include those from like your skin, cholecalciferol, those from the digestive canal, secretin, cholecystokinin, HCG from the placenta. That's actually what's tested for when a female pees on a stick to find out if she's pregnant. And we'll talk about a good number of these hormones later in the semester, but we've already covered, like 25 hormones, so I didn't need to add 10 or 15 more to your list. We won't talk about all of them. Like, we don't really talk about the skin much in this class, so we won't really talk about cholecalciferol, but we'll talk about, most of these from the digestive system. Talk about HCG, estrogens, and progesterone when we get to the reproductive system. And so there'll be a time in the semester where I'll say, remember that slide where there was a hormone listed and I told you we talk about it? You'll hear me say that. And that'll be at various points as we get towards the end of the semester. Okay, I'm gonna stop here. It's a nice spot to stop.